All right, today we're diving into a really radical new idea, one that might just challenge everything we think we know about the universe. What if gravity isn't what it seems? What if that massive 95% of the cosmos we've labeled dark matter and dark energy is just a grand illusion?
For decades, one of the biggest headaches in cosmology has been this giant mystery. All our observations, everything we see, tells us the universe is packed with stuff we can't detect, dark matter, dark energy, making up a truly staggering 95% of everything out there. But what if it's not missing at all? What if the problem isn't with the universe, but with our theory of gravity?
So if you're going to look for a new theory of gravity, you have to start where the old ones break down. And right now, there is a deep, fundamental crack running through the very foundation of modern physics. It's this major conflict between our two best and yet totally different ways of describing reality. See, on one hand, you've got Einstein's general relativity. It's beautiful. It works perfectly for planets, stars, galaxies, the big stuff. But on the other hand, you have quantum mechanics, the undisputed champion of the tiny subatomic world. The problem? They are completely, utterly incompatible. They don't speak the same language. They describe two totally different universes. And that is the crack in cosmology that keeps physicists up at night.
So how do you possibly bridge a gap that big? Well, a new idea has entered the ring. It's called the Hypothesis of Dispersive Oscillations of Vacuum, or HDOV for short, and it proposes a pretty fascinating solution, suggesting that gravity might just have a hidden trick up its sleeve.
The whole theory really hinges on this idea called functional inaccessibility. And what it says is that when space-time gets super curved, we're talking near a black hole or during the crazy expansion of the early universe, it doesn't actually destroy information. No, instead, it disperses it. The best analogy is trying to look at a coin at the bottom of a rippling pond. The coin's still there, right? But its image is so scattered and distorted by the water that you just can't make it out. HDOV suggests gravity does something just like that, but to the very fabric of information itself.
Okay, so hiding information sounds a little like cosmic magic. How does it actually work? Well, the theory gives us a new little piece of math to play with, and it comes with a really great intuitive picture.
At the very heart of this is a parameter called eta p. And honestly, the best way to think about it is as the universe's dimmer switch. But instead of you controlling it, this dimmer switch is controlled by the strength of gravity. So here's the chain reaction. First, you get some gravity from a huge star, a galaxy, whatever, and it curves space-time. As that curvature gets more intense, it turns up the dimmer switch. That eta p parameter changes. This, in turn, causes information to get scattered or kind of projected into a subspace where we just can't measure it. And here's the absolute kicker. From our point of view, this loss of information creates an illusion. It creates an effect that looks exactly like the accelerating expansion of the universe, the very thing we invented dark energy to explain. HPODV says dark energy isn't some weird substance. It's a geometric illusion caused by gravity hiding information from us.
Now, a radical idea is one thing, but this is science. It has to face the music. It has to go up against the evidence. So how does HDOV actually hold up when we put it to the test? To find out, we have to pit it against the reigning champion, our current standard model of cosmology, known as lambda CDM.
Round 1 of the trial. Exploding stars, specifically Type 1a supernovae. These things are incredible tools for astronomers because they always explode with the same amount of brightness. That makes them perfect standard candles, which lets us measure vast distances across the universe and see how fast it's expanding.
So, who did the data favor? When scientists compared how well HDOV and the standard model fit the actual supernova observations, HDOV came out on top. They used a statistical test called the BIC, which basically gives points for accuracy but subtracts points for being overly complicated. In this world, a score difference of over 10 is considered very strong evidence. HDOV's score, it beat the standard model by a whopping 10.5.
But hey, a new theory of gravity can't just explain the distant universe. It's also got to work right here in our own backyard. This is a huge hurdle. So they checked it against classic tests like the strange little wobble in Mercury's orbit and gravity data from the Cassini space probe. The result? It passed with flying colors. Just like general relativity, it gets our solar system exactly right.
For the final test, we're going to the most extreme places you can possibly imagine. The chaotic moments right after two black holes smash into each other.
Now here's the really cool part. After two black holes merge, the new, bigger one wobbles and rings like a giant cosmic bell,
sending out ripples of gravitational waves. This is called the ring down. And HDOV predicts that the sound of that ring down should be just a little bit different than what general relativity predicts. We're talking about tiny, subtle modifications in these gravitational echoes, but they're specific, a unique signature that our newest gravitational wave detectors might actually be able to hear.
So let's step back. We've got some strong statistical evidence, and it's passed a few really crucial tests. What does this all mean? Well, if HDOV is even close to being right, it could fundamentally rewrite our entire picture of the cosmos.
And here's what makes this real science and not just a fun story. It makes clear, testable predictions. This is the absolute hallmark of a good theory. It's basically saying, here's how you can prove me wrong. It says, go look at really, really distant galaxies, and you should see the expansion of the universe looking a little different. It says, listen closely to those black hole mergers, and you'll hear our unique signature. And get this, it even predicts effects we could look for in tiny tabletop quantum experiments. It gives us a roadmap to either confirm it or throw it out.
So what's the big picture here? What HDOV is really offering is a whole new way of thinking. It's a way to potentially get rid of the need for all that mysterious dark stuff that supposedly makes up 95% of our universe. Instead, it offers a new principle, that the very geometry of space-time, it determines which parts of reality we can even access or measure. It means our reality isn't some fixed, static backdrop, it's a projection, and gravity is holding the projector.
And this leads us to the final, really mind-bending question we have to ask ourselves. Is the universe we see the whole story, or is it just the part of the movie that gravity allows us to watch? It's a profound thought because it suggests that the deepest cosmic mysteries might not be hiding in some exotic new particle, but in a completely new understanding of the nature of reality itself.